Hello, my name is Chris McGrath, and I'm applying for the position of physics instructor at Washington and Lee. I'm happy to be presenting to you today this video lecture about electric potential energy and electric potential corresponding to Reese sections 17.1 to 17.3. I'd like to thank Professor Masalou for allowing me to present to you in this format. This is a format that I've been using with my students for about 7 years now, and it's my preferred method of delivering content. This mode of instruction is often called a flipped classroom. The chances that you've experienced this are pretty good at this point, I think. A lot of folks are using this kind of instruction. And just a few words about that before we get started. In a flipped classroom, the thing that's getting flipped is that the content that would be traditionally delivered in the form of a lecture given in the classroom is delivered via a video, podcast, or something like that. In this case, I'm delivering the content to you in the form of this video. And when students are in class, they will then work on the things that they typically would have worked on outside of class. So the homework problems you can work on in class. So the flip is the content and then what would have been done outside of class. Those are being flipped. I'd like to give you a few pointers about how best to interact with a content video such as this one. I would like you to still take notes, just like you would if this was a traditional presentation of a lecture. But because the video can be paused and because you can rewind if you need to, it changes a little bit the way you can interact with it. And to get the most out of the video, I'll recommend that you use those features, the fact that you can pause, rewind. For a lot of my students, they really like the fact that they can focus on the presentation of the content, and then when we get to the end of a slide, for example, you can write down whatever notes you need to write down from that slide so that you don't have to be distracted by trying to write down the content while also paying attention. I'll confess to you that for me this would have been a very desirable feature that I did not get in my classes, my science and my math classes. I was not a good note taker. I always felt like I really wanted to pay attention to what was happening in class and really focus, and I couldn't do that and write things down at the same time. So of course I always had my textbook at home that I could go back to and I could make my own notes after the fact. But here you can have the best of both worlds, so to speak. You can watch the content and then pause and write things down. So I would recommend that you take advantage of that. All right, let's move on to the lecture now. I want to start by just reviewing a couple things that you already know from Chapter 16. First, in Chapter 16, you encountered Coulomb's law for the first time, and Coulomb's law is our quantification of electric force. When we have two charges, Q1 and Q2, the magnitude of the electric force that they experience is an inverse square relationship. In other words, it depends on the inverse square of the distance between those two charges. And if we think about those charges as being movable, then the only thing in this right side of this equation, the only thing that's really variable is this distance between them. So the magnitude of this electric force depends only on the inverse square of the distance between them. Of course, it depends on Q1 and Q2. The magnitude and the direction of the electric force will depend on the signs of these, whether they agree with each other, in which cases the forces will repel, or whether they're opposite each other, in which case the forces, they'll be attractive. I'm sure that it's been pointed out to you that this definition for electric force in Coulomb's law here looks a lot like the universal gravitational force, which is also an inverse square law. Depends on the magnitude of the two masses, but really depends on the inverse square of the distance between those two. So we might have two different masses, but here we call this an inverse square law because it depends on the distance between those two charges. Remind you also of the definition of the electric field. The electric field is how much electric force we would have if we placed a charge in that electric field. That's how much electric force we have per charge. And the units for that electric field are newtons per coulomb. If the electric field seemed like a new and different kind of physical concept or construction, to also remind you that this is similar to, it also has an analogy in gravitation. If we find the gravitational acceleration that a body feels because it's near another one, that looks just like this, but we've divided out one of the masses, just like we divided out one of the charges here. And although we usually think about this as an acceleration, we might think about the units as meters per second squared, those units are equivalent to newtons per kilogram, and that makes a much stronger analogy to the electric field. In that way, we could think about this gravitational acceleration as the gravitational field strength, and we could see that the units are newtons per kilogram. If we think about here, we have a force measured in newtons, and if we divide out one of the masses, would have that force divided by kilograms. Locally, we have a uniform gravitational field at the surface of the Earth, and here our 9.8 meters per second squared, which we usually think of as gravitational acceleration, is, we could also think of that as 9.8 newtons per kilogram. We get 9.8 newtons of force per every kilogram we place in that local gravitational field at the surface of the Earth. So it may be helpful to understand that analogy as well. And a couple things that you already know from your mechanics course, Physics 111, that we're going to use in this lecture here. The definition of work. Work is the integral from an initial to a final position of force with respect to displacement. So that's the force dr, and that's a dot product. And this is the work done by that force in moving an object from that initial to final position. For conservative forces, we know that work is path independent. And that means that whatever initial and final positions you have, it doesn't matter how you get from that initial position to that final position. The work done by that force, if it's a conservative force, the work done by that force will be the same, regardless of what path you choose from initial to final. And I'm pointing that out here because that's going to be important for us in a few minutes. Also, for conservative forces, we know that work is equal to the opposite of the change in potential energy. And that, I think, maybe is best illustrated by just a simple example here. So if we take a mass here that's at the level of ground, we'll consider this to be height 0, and it's moved up to a height h. You know, I'm sure you remember that the change in potential energy of this mass is equal to mgh. And it's not delta h here, I just have an h here because we started at h equals 0 and we moved up to a height h. So the change in its potential energy, it goes from having none at height 0 to mgh. Now the work done by the gravitational force, which is a conservative force, is this dot product here. I didn't write it in integral form because it's a constant force, so it would just reduce to this. And that's negative mgh. Why negative? Well, let's bring up my pen here. The gravitational force is directed downward, and the displacement through which this mass is moving is directed upward, anti-parallel, in exactly the opposite direction to this. And for that reason, the dot product here is going to give us a negative result. So we can see here, this is just an example of, for a conservative force, that the change in potential energy is equal to the opposite of the work done by that conservative force. And also, just to reinforce the path independence here, if we had instead moved the mass to the same location but through a different path, that none of this would change. The change in potential energy would still be mgh, and the work done by the gravitational force would still be negative mgh. So that is path independent. Now, electric force is a conservative force, just like universal gravitational force is. And we can easily convince ourselves that that's true because of the similarity in the forms of Coulomb's law, which defines electric force, and Newton's law for universal gravitation. Those were both on that earlier slide. They're both inverse square laws. And if this is a conservative force, then surely so is electric force. So that's good news for us. We can use those facts about conservative forces. So here's the definition of work again. It's the integral here from an initial position to a final position of force.dr, and that's equal to negative potential energy. So I'm just combining those two equations here. And since the electric field is equal to the electric force per unit charge, we could rewrite that, just multiply both sides of this equation by Q. We could write it in this form here. And since we're only going to be talking about electric forces here, I did drop the subscript of the E here, but this is an electric force. You can add that subscript in if you feel that's helpful for you. So now I'm going to go ahead and substitute into our work integral here. I'm going to substitute this in place of force. And since Q, that charge is constant, we can move it outside the integral. So that integral for work looks like this. And on this side, I have the negative or opposite of the change in potential energy, which I wrote out here as potential energy final minus potential energy initial. And if we divide both sides of this equation by the charge Q, like so, then we have a new and interesting form of this equation. Here we have a nice integral. This is just the integral from an initial to final position through an electric field along some path. And here we have that it's the opposite of the change in this quantity, potential energy divided by charge. So many times in physics, you've already seen that when a new concept or a new quantity presents itself like this, we're often tempted to define this quantity and give it a new physical name. And that's exactly what we're going to do here. Since this quantity is showing up here in this equation, we're going to define V. This is the electric potential. This is our definition now. Electric potential is equal to potential energy divided by charge, just like electric field was equal to electric force per unit charge. So in much the same way, this is how much potential energy we would have if we placed a charge of magnitude Q, if we place that charge in that electric field. Now the units here, this is potential energy. We've got a charge, so that would be joules per coulomb. That would be the unit here. And you've seen this happen before too. This is a unit that comes up so often that it's going to get its own name. It's the volt, and we're going to use a capital V to represent that. Just like with potential energy, this depends on our choice of ground. So when we talked about our mass moving up through that height h a few minutes ago, that depended on us defining h equals 0 at that ground level. And similarly here, we're going to make our choice of electrical ground, where V is equal to 0. And you can see from this equation here, where V equals 0, that's where potential energy is equal to 0. So those are going to be equal to 0 at the same location. We have to choose that, and we'll make some particular choices that will make things easy and sensible. We'll talk about that in a few minutes. And here I mentioned already the similarity between this relationship here and the relationship between electric force and the electric field. But I'd like you to have that in your notes. So if we know the electric field, then we know we can find electric force just by multiplying the electric field by the charge we're going to place in that electric field. Then we can know what that electric force would be. And similarly here, if we know the electric potential at some location, then the potential energy of a charge that we place in the electric field, which has this associated electric potential, that's equal to the charge times the electric potential. And maybe just to point out and re-emphasize that electric field does not depend on a charge being in the electric field. Electric field is waiting for a charge to come along and be in that electric field. Likewise, electric potential is electric potential for a location in space. There's not necessarily any charge there, and if we do place a charge there and we multiply by the electric potential, then we have the potential energy. Now, would also like to define the delta V, the change in electric potential. We're going to call that potential difference, delta V. And if you look up just a little bit in your notes, it was the last thing I had on the slide previous to this one. Instead of having that PE final over Q minus PE initial over Q, we're going to write that as delta V, since we've now defined the electric potential. And I've moved the negative sign to the other side. This is how we usually see this equation written. So delta V is equal to the opposite of this integral from an initial to final position through the electric field, dr. And I'm going to go ahead and put a little box around this equation, more or less a box. You can be generous here, and we'll call that a rectangle. And also our definition here of electric potential. I'm putting boxes around those. These are the kind of highlights of our notes here. When you look back at these notes and you're looking for like what were the big results, I think these are two of the things you'd like to have your attention drawn to. All right, if you'd like to keep track of what sections we're on in the book, so far that was section 17.1, and the electric potential of a point-like charge Q, this is section 17.2 in your Reese textbook. So from chapter 16, we know that the electric field associated with a point-like charge Q is defined like so. And you notice that this looks just like Coulomb's law, but we've divided out one of the charges. So here, this is the electric potential of, this is the electric field associated with a point charge. And you know what that looks like from chapter 16. If we place a point charge, if it's positive, we'd have electric field lines radiating outward from that charge. And if it's a negative charge, they would be pointing radially inward, that charge. And the magnitude of the electric field would become weaker according to the inverse square of that distance. Now we need to choose ground. We need to choose the place where the electric potential is going to be equal to 0. So for a point-like charge, we're going to choose that ground where electric potential and also where potential energy are equal to 0 at r equals infinity. That might seem like an odd choice, but if we look at the definition of the electric field here, because it's this inverse square law, we're only going to get zero electric field around this point charge Q as r approaches infinity. There's no way to actually make this equal to zero, but as r approaches infinity, this will approach zero. So if we want to choose a location where our potential difference is equal to zero, our electric potential is equal to zero, then we're going to choose that ground where r is equal to infinity. And maybe just to make it seem a little less weird, remind you that when you learned about universal gravitation, we made the exact same choice, that universal gravitational potential energy is equal to zero at r equals infinity for exactly the same reasons. Okay, so that means that our potential difference, which is equal to this is just a restatement of what we have in that last box from the previous slide. So now I'm going to replace that electric field here with what we know the electric field to be around a point charge Q. So our constant we've taken to the outside of the integral, and then we have this maybe confusing jumble of r's here. So let's take a look at an example here. So this is, if I advance to the next slide at any point before you're ready, of course you can pause the video and jot down what you need to jot down. I'm going to go ahead and advance to the next slide. Now, what we'd be talking about is that potential difference. We're talking about that potential difference between two locations in space. Let's say a location here and a location here. And these locations are in the vicinity of a point charge, Q, right here. So that integral we need to get from this initial to this final position. So maybe the first thought we would have is we could just draw a straight line from here to here, and we could try to integrate along that r displacement. And we could do that. It wouldn't be horrible, but there's an easier way to deal with this. Because of path independence, we can choose any path that we want that gets us from this initial point to this final point to calculate the potential difference between them. So we're going to break up the path into two bits. The first one, we're going to follow this circular arc here from the initial position along that circular arc with radius ri until we get to the rf vector. And the reason we're going to do that is because along this path, the potential difference is equal to zero. And I'll ask you to think just for a minute about why that would be true. So here, another thing we can do in these video presentations, I can ask you to pause and think about that for a minute, and you can take your time, think about it for as long as you like, and I'll ask you to do that now. Think about along this circular path here, this segment of this, or this arc of this circle here, the potential difference is equal to zero. So I want you to pause the video and think about why that would be true. Are you back? Did you really pause and think about it? Give you another chance. Okay, I believe you that you paused now. So why is that true? Well, potential difference depends on the separation between this charge and the location in space. And along this circular arc here, that value of r does not change. It's constant. So for every point along this circular arc with the same distance, the same radius r from that point charge Q, the potential difference is the same. So it doesn't change along that path. You could also think about why this is zero along this path. As we integrate along this path, because that integral is a dot product, everywhere along this path, let's say we're here on the path, in this direction here, well, if this was a positive point charge, the electric field would be radially outward from that. And if we move to a different location, would be going in a slightly different direction, but so would the electric field. And everywhere along this path, the electric field and the direction we're moving along this path would be perpendicular. So that dot product all along this path would be equal to 0. So first part of our path, the value of the integral is equal to 0. And then for the second part, we're going to move to our location here out to, sorry about that, out to our final location. And that is, give me the benefit of the doubt, that's a straight line, I promise. So we moved out to here. The integral along this path was 0. And now we're going to move straight along this r vector, the rf vector. So what does that mean for us here? It means that along the first part of the path, the integral was 0. And the second part, now this is just a one-dimensional vector. So we just need to go from, we need to integrate from this ri. Notice this is not a vector. This is just the magnitude of ri. That's the magnitude right here, this displacement. And we need to get from there to here, to rf. And that's a nice little one-dimensional integral, no problem. So what's the antiderivative of 1 over r squared? That's negative 1 over r. I'm going to make our substitutions here. The negative signs are going to cancel out, and we arrive at this result here. So our potential difference between two locations is equal to this expression. And we made that easy for ourselves. We made the calculus easy by choosing a path that was easiest. So our potential difference between two locations in the vicinity of a point charge is equal to this expression here. Now, since our ground is at r equals infinity, that means we could use the expression that we just found there. So our potential difference, our electric potential at infinity minus our electric potential at some location in the vicinity of that charge would be equal to, substituting that into our last expression. This is a little bit cavalier, just plugging infinity in. What we really mean, this is really the limit of 1 over r as r approaches infinity. But we know that 1 over something that's approaching infinity, this is going to go to 0. And again, we're going to have a negative sign here. We know that this is equal to 0. That's our choice of ground. So this is 0, and this is 0. Our negative signs here will cancel out. So the electric potential at some point r in the vicinity of a charge q is defined like so. And just want to emphasize here that this is r to the first power. That's not a mistake. So there's the potential confusion, sorry, that's a bad joke there, to look at this and think that it looks like the definition of electric field, or maybe like Coulomb's law, and be tempted to make r to the second power here. But this is, in fact, supposed to be just r to the first power, and that's because of our integration that happened just a little bit above there. So this deserves a little box around it too, I think. All right. And this corresponds to section 17.3 in your Reese textbook. And if you look in the book, it's a very short section. It's about a paragraph. And it's going to present, or we're going to present here, that since electric potential is a scalar, then the total electric potential, V1 plus V2 plus V3, because of some collection of point charges, is just the algebraic sum of the potential differences. Sorry, the electric potentials. 1, 2, and 3, however many you have. And if we wanted to write that out according to what we just have in our last box, then that V total, if we factor out our constant here, is just our constant times Q1 over R1 plus Q2 over R2, and so on. And I just want to make sure that you understand what these R1s are. So let me just make a quick sketch here for you. So if we had here a charge, we'll call this one Q1, and another charge here, Q2, then remember that our electric potential is not another charge. We're talking about a location in space. So let's pick a location, let's say here. So what is the electric potential associated with this location in space because of its proximity to these two charges? And this distance from our charge Q1 to that point in space, that's R1. And this distance from our second charge to that same location in space, that's R2. So notice here that to find the total electric potential, there's no distance between these two charges. That's not part of our equation here. So this R1 is the distance between the location at which we're calculating the total electric potential. That's what this R1 is, this R2. These are just the positive distances between our location and our charges. The sign of our electric potential, it certainly can be negative, but that's going to depend on the signs of our charges, not on these. These are just the magnitudes of the separation between our charges and the location at which we are calculating the total electric potential. And this is the last slide of the presentation. I hope you enjoyed that lecture. I hope you made the most of the pausing and rewinding and everything that you can do with a lecture presented in this format. I look forward very much to seeing you all in class at 9 o'clock. I guess your class starts at 8, but from 9 to 10 will be my part of the class. And during that time, we'll work through some problems, maybe make some presentations of solutions, and get to know each other a little bit. And I will see you then. Thank you.